Hi everyone! Over the next two videos, we are going to extend the capabilities of our I/O implementation so that it can execute actions concurrently. I hesitated for a long time about including this section or not. On the one hand, it's probably the most useful and powerful aspect of I/Os, and it shows how I/Os can completely replace features from the standard library. On the other hand, some of the techniques we are going to use are mind-boggling, which means that it may take months or years before you feel comfortable thinking this way. So you should really consider these videos as bonus material. You will probably learn a lot of interesting ideas from them, but it's unlikely you will be able to follow every single step, at least not the first time you go through it. So let's start by reviewing our implementation of from-to clients, the method that creates a search flight service by querying two data providers and aggregating their results. I simplified the code slightly. The most important point is that we combine the two searches using a for comprehension. Now, in your opinion, how is the code executed? Please pause the video and think about it for a minute or two. From-to clients is sequential, meaning that it only sends a request to client 2 once the request to client 1 has completed. How do I know that? When we call search by client with client 2, we already have access to the result of search by client with client 1. So if we have access to the result, it means that the operation must be complete. There is no other way. More generally, all lines within a for comprehensions are executed sequentially, which kind of makes sense because map and flat map are by nature sequential. They both give us access to the result of the I/O and let us do something with it. Okay, so if we can't use a for comprehension to execute I/Os concurrently, this means that we'll need to create specific methods for this use case. Let's start with the simplest possible scenario where we only need to execute two I/Os concurrently. This method is often called parzip. Parzip is a method on the I/O class which takes an I/O of other and returns an I/O of tuple A other. We also need an execution context in order to dispatch these two tasks to a thread pool. So the idea with parzip is to take two I/Os, dispatch their execution, wait for both results, and repackage it in a tuple. If you wonder why it's called parzip, it's because it behaves like the method zip, but instead of executing two I/Os sequentially, it executes them concurrently. And concurrently means that we are making progress roughly at the same time. For example, we may execute the first I/O for a bit, put it aside, execute the second I/O for a bit, and then go back and forth between these two tasks. While parallel will mean that we are running both I/Os at exactly the same time. For example, over two different CPUs. So there is a tiny difference between parallel and concurrent. But to be honest, most of the time we use these two words interchangeably. So the real difference is between sequential and concurrent or parallel. Let's have a look at an example. Here I define the method stream, which prints a message to the console, sleeps, and then repeats this a few times. For example, stream A will print a message task A0, sleep 200 milliseconds, then print task A1, sleep 200 milliseconds, and so on. Now if we combine stream A and stream B using zip, we see all messages for task A and then all messages for task B. This shows that zip is sequential, as stream B only starts when stream A is complete. Now if we combine stream A and stream B using parzip, we see both messages like task A, B, A, B, A, B, which show that parzip executes the I/Os concurrently. And the order is not deterministic. If we run it a few times, the messages will be interleaved in different ways. Now the million-dollar question is how can we implement parzip? I suggest that we get some inspiration from Scala features in the standard library because we know that they can run code in parallel. So let's come back to our flight aggregator problem, but this time around let's say that search flight client uses feature instead of I/O. In this case, How would we search with both clients at the same time? First, we'll call search for client 1, assign the result to a variable, and then repeat the same process for client 2. After these two lines are executed, both requests to client 1 and client 2 have started, as you can see on the diagram on the right. Then we can use a for comprehension to describe how to combine the results of the futures when they become available. One thing to note is that we don't know which client will complete first. The only guarantee that we have is that the aggregation logic will run after both clients have returned successfully. We can use a for comprehension to combine futures concurrently because the futures have been started outside the for comprehension. However, if we had started the futures inside the for comprehension, then we would execute them sequentially. This is one of the most common pitfalls of the future API. And one way to sidestep this issue is to use the method zip instead of a for comprehension. Zip will start both futures concurrently and give us back a tuple of the results. Then we can use map to run the aggregation logic. This version of the code may be less readable, but at least we are guaranteed that both futures will run concurrently, even if we extract or inline the futures. For example, these two versions of the code produce exactly the same result. Okay, so now we should have enough background information to implement parzip. Let's go back to the file io.scala in the package exercises.action.fp. Toward the end of the class, you should see the method parzip. So please pause the video and try to implement parzip using everything we have learned about Scala futures. This means that it is completely fine to use futures within the implementation of parzip. And also don't forget to enable the test. Okay, so first thing I suggest is that we go to the test file and enable the tests for parzip. And let's have a look at what they do exactly. So they use a mutating variable technique that, by now we are pretty much familiar. So we start counter initiated to 0, and the first action now is a bit more complex than what we had before. The first thing it does is that it calls io.sleep with 10 milliseconds. So this is going to take the current thread and ask it to do nothing for 10 milliseconds. So if you look at the implementation of sleep, it just codes thread.sleep, which is highly inefficient, but it will work for our toy IO implementation. So we ask the current thread to sleep for 10 milliseconds, and then we increment counter by 1 and returns it. While the second action immediately multiply counter by 2 and returns it. So what we do then is that we combine first and second with parzip. So this should execute both first and second concurrently. We expect both of them to start at the same time. But because there is a sleep in the first action, we expect it to be slightly delayed. So we expect second to execute first. This is why here, when we run the action, we expect it to see 0 on the right-hand side of the tuple, because counter times 2, when counter is equal to 0, 2 times 0 is 0. And then the first action will execute, which increment counter by 1. So we expect that because they are both run concurrently and second is faster than first, we expect second to execute first and then first. While the second test does the same thing, but it just moves where sleep occurs. So now sleeps occur in the second action, which means that we expect first to execute first and second to execute after. And as you can see now, the result is different. Now we expect to see 1 and 2 because we expect to see counter incremented first by 1 and then multiply by 2. And by the way, these tests are a bit flaky, so they should work fine on your machine, but on CI they may not. This is because of the thread.sleep. It's really not, it's not really great for testing. But at least it should work on your machine. So let's enable the test. So we enable the test, but let's try to first implement parzip using zip. So we'll just say, let's say that parzip will be implemented sequentially just to check that the test should fail, or at least one of them should fail. Yes, so the first one fails because Zip executes the I/O sequentially, which means that first will be executed first and then second, which means that we got 1 and 2 instead of 1 and 0. So if we manage to implement parzip concurrently, this test should pass. So let's do that right now. Okay, so how do we implement parzip? So we need to create a new I/O, because this is what we need at the end, and we need to return a tuple A other. We don't really need this type annotation. This is more to guide us toward, like, what are we looking for. And the first thing we want to do is to dispatch the execution of both the current I/O and other to the thread pool. And to do this, we're going to use future. So we'll say, let's create a future. Let's call it future 1. That will be a future of A. And what it's going to do is that we'll do this dot unsafe run. So we are going to execute the current I/O using the future API, so it's going to dispatch it to the thread pool. And by the way, we need to specify the execution context. We'll do the same for other, and this will be a future of other. So after these two lines are executed, both computation will be dispatched to the thread pool. Now we need to combine the results together. So we're going to use zip from the future API. So we'll say zipped is future 1 zip with future 2. And the type of zip is a future of tuple A other. So we are really close to what we want. Now this zip future is basically something that says eventually we'll get a value of type tuple A other. But we don't know when it will be complete. At some point it will be complete. Now the problem is that within the I/O constructor we need to get the real value at the end. So we need to get the tuple A other. So the only way to transform this future A other into a tuple A other is basically wait for it. So we need to say await.result, where we'll pass the future. And here we need to specify a duration, like a timeout. But because there is no meaningful timeout, we'll just say duration inf to say that we basically wait forever. Cool, so let's run the test to see if it works. Yes, it does. Awesome. So both parzip tests now pass. Okay, so now that we have parzip implemented, let's go back to search flight service and let's change the implementation of from to clients. So could you please pause the video and refactor from to clients so that both requests to client 1 and client 2 are executed concurrently. You may need to change slightly the API of from to clients. You may need to add an execution context, for example. So please pause the video and give it a try. Okay, so the real problem here is how we combine the I/Os together. The fact that we use a for comprehension, and we have seen in the slide that for comprehension is always sequential. So if we want to combine the I/Os concurrently, we need to use parzip. So what we're going to do is that we'll take the first I/O, then we'll use parzip, pass the second I/O, so search by client with client 2. These require an execution context, so we'll need to ask also an execution context in from to clients. So we'll say, okay, I also need to get an execution context here, and I will pass it to parzip. Then parzip gives us back an I/O of a tuple. So this means that we can map and do a pattern match to have a look at the two values. So here we get a tuple list of flights. So the first argument of this tuple is the list of flights from client 1, and the second argument is the list of flights from client 2. So let's do this, and then let's copy the aggregation logic. So as you can see, the code using parzip is not as readable as a for comprehension. I think for comprehension is very difficult to beat in terms of readability. But now the benefit of this is that with parzip, both actions are executed concurrently, which means we don't have to wait for the result for client 1 before contacting client 2. So it's much more efficient. Now most likely our test will be broken because we added an extra parameter. So let's have a look. Yes, indeed. So you can see now we need to add an execution context. So what we can do, we could create an execution context in our test, or we can just use the global one. That's completely fine. That's it. Okay, so now that we have our test that pass, okay, so let's run the test. Cool, it works. Cool, so that's great that all our tests are passing, but it will be nice to visualize this concurrent execution with parzip. So to do this, I created an application called Concurrent Examples, and it's located in the package exercises.action.fp.concurrent. So please open it. And basically in this file, the goal is to combine a couple of IOs together, either sequentially or concurrently, and visualize how it works. So the first thing we do in this file is to create a thread pool with a fixed amount of thread, currently just 4. Then we'll run the IO par2, and par2 what it does is that it combines 2 IOs concurrently using parzip, and each IO is going to print a message to the command line, sleep, and do that repeatedly. So exactly like what we've seen in the slide. So let's run this application. Great, so as you can see, we see both messages for task A and B are interleaved. So this means that both IOs are executed concurrently. We can even see that task B are executed on thread number 1, while task A are executed on thread number 0. Now, if we rerun this same file, but with sec2 instead of par2, now we would expect to see all messages for task A and then all messages for task B, because sec2 uses zip instead of parzip, which is sequential. Great, so this is exactly as expected. We can see all messages for task A and then all messages for task B, and we can even see that all of them were executed in the main thread. Cool, so now that we can run 2 IOs concurrently, the next logical step is to run an arbitrary number of IOs concurrently. So let's go back to the IO class, and you will see in the companion object there is a method called parSequence and also parTraverse. But parTraverse is already implemented because it's basically an alias of a parSequence of map followed by parSequence, similar to how traverse is an alias for map followed by sequence. So the only method we need to implement is parSequence. And parSequence basically behaves like sequence, but every IO inside the list is executed concurrently. So the idea is to start the execution of all IOs and then wait for the result to be ready. Then parSequence will repackage all the results in a list, which is guaranteed to be in the same order as the input list. So this probably sounds very complex, but we have the main parts of the puzzle available. We know how to execute 2 IOs concurrently with parzip, and we know how to squash a list of IOs sequentially with sequence. So it's likely that parSequence will be a mix of sequence and parzip. So please pause the video and give it a try, and don't forget to enable the test. Okay, so again, first thing we're going to do is to enable the test for parSequence and parTraverse. So let's have a look at parSequence, what it does. We again use this mutating variable technique, where we start counter with 0, and we have 3 actions in the list. So the first action sleeps for 10 milliseconds and then multiply counter by 3 and returns it. The second action immediately bump counter by 2 and returns it. And the third action sleeps 50 milliseconds and decrease counter by 1 and returns it. So if all 3 actions are executed concurrently, we expect the second action to execute first because there is no sleep. So we expect counter to be equal to 2. Then we expect the first action to be executed because it's 10 milliseconds. So we'll expect to multiply it by 3, which will be 6. And then the third action will be the last because it sleeps for 50 milliseconds. So we expect it to be 5, 6 minus 1, 5. But if the actions were executed sequentially, it will be first 0 times 3, 0, plus 2, 2, minus 1, 1. So we can see that the first thing we could do is to first implement sequence, a parSequence using sequence, and we'll see that the test should fail. So let's run them again. So we say IO test. Cool. So now, yeah, we can see parSequence and parTraverse fails exactly as expected. We expected to see 6 to 5, but we got 0 to 1. This is because at the moment par sequence is sequential and not concurrent. So let's try to fix that. So what we can do is first start by aligning the definition of sequence, because we know that it's going to be roughly similar. We want to run every single actions and combine them concurrently. So really the only thing we need to change is this part. This part is how we combine the IOs together. Currently we combine them sequentially with a for loop, and we want now to combine them concurrently. So we probably need to use parsing. And actually, what if you squint at it, if you look at this code carefully, you realize that we could re-implement this code using zip. So we could have implemented this way. We could have said state zip action. So this would have given us a tuple. So this was called result1 and result2. And then we could have copy-paste this aggregation logic. I have a typo. OK. So actually, let's copy-paste this code, and let's change the implementation of sequence just to check that if it actually is the same thing. So let's rerun the test, and we'll see if the code of sequence is passing. Yes, it does. So sequence is fine. Par sequence is still sequential. So really, the only thing we need to change here is this code. At the moment, we zip sequentially the state, which is a prefix of the list, and the current action. What we want to do is to zip them concurrently, so execute both IOs concurrently. So we'll need to pass also an execution context, which we have as input. Let's rerun the test. Nice, it works, awesome. Now that we're able to run multiple IOs concurrently, let's go back to search flight service, where we'll try to update from clients. So from clients currently execute each client's request sequentially. This means that it sends a request to client 1, and when it gets the results, it sends a request to client 2, and so on. As you can see, this is extremely inefficient. If we have 29 clients, as was the case with Skyscanner, and each client takes 200 milliseconds to respond, it will take us around 6 seconds to produce a result for our users. This is unacceptable. So the idea is to update from clients so that all clients' requests start as soon as possible. So please pause the video and try to refactor from clients, and you may need to change slightly the signature. So please pause the video and give it a try. Cool, so here really the change is very minimal. We only need to change traverse to par traverse and also add an execution context in front. So let's call it EC. We'll pass EC here, and that's it. Now, this is the only change that we need to do in order to execute every single client's request concurrently. It's pretty nice, isn't it? Now we'll also need to update the test, so we'll need to do the same thing we've done before. We'll need to pass an execution context. So we'll just update all the constructors, and let's rerun the test to verify that it works. So it's very weird. It seems that our tests are hanging, and actually if you rerun it a couple of times, it may be fine. So let's rerun it just to check. I've done it a couple of times before. Sometimes it hangs, sometimes it doesn't. So you can try on your machine. So maybe to understand what is going on, what we could do is to go back to concurrent examples here, and instead of running sec2, let's run par_many. So par_many is an IO that uses par sequence. So we are taking several IOs that print stuff to the command line, and we combine them together using par sequence. So let's try to run this IO to see what is going on. So that's really weird. It seems that it's running sequentially. We see like first the F, and then the D, and then the E, and they all run on the thread number 3. So it seems that the other threads are not used somehow. And also what's very weird is that it seems that the test is hanging. It's not finished yet. For example, normally we expect to see a message at the end. For example, if we rerun part 2, we expect to see some kind of termination message at the end. So for example, with part 2, once it's done, we should see this process finish at the end. So this, we can see that the I/O is done. But when we rerun, if we rerun par many, this doesn't happen. We see a couple of tasks being printed. First, not all of them. We see the F, the D, and the E, but we don't see the A, B, and C. And we don't see this termination message. So this is very weird. So what we could do maybe is to try to modify the thread pool size. So for example, if we double it, if we put like 8 threads instead of 4, let's rerun it. Wow, so that's extremely weird. Now, it actually runs concurrently. We can see that we see the C, E, F, this is interleaved, and we can see that they run in different threads. We see thread number 3, thread number 6, thread number 4. So it seems to be working, kind of fine, and the process terminates at the end when the pool is big enough. So let's try to experiment a bit more, maybe with a smaller thread pool, so let's say just only 2 threads, and let's rerun it. And this time, nothing is printed, so nothing is executed at all, and it's completely stuck. So in your opinion, what do you think is going on? Could you please review the code of parsequence and parzip and try to figure it out? So it turns out that the problem is with parzip. Because parzip is blocking, because it calls the method await.result. This means that the 2 tasks are sent to execute in the background, and the thread where parzip runs is blocked until both futures are complete. So this works fine if we run a single parzip operation, and we have more than 1 thread in the thread pool. However, it's a serious concern for parsequence, because it calls parzip recursively. If you think about it, parsequence builds like a tree where the leaves are the meaningful operation we wish to execute, and the trunk consists of all the parzip's operation between I/Os. As you can see, our current implementation of parsequence is horrible because it needs to block 3 threads in order to execute 4 tasks concurrently. This also explains why parsequence can get stuck. If the thread pool is bounded and the list of actions to execute is long, then we may arrive at a point where all the threads in the pool are blocked, and the only way to unblock them is to execute actions in the work queue. In other words, it's a deadlock. Now, even if we manage to rewrite parsequence to block a single thread, it will still be disastrous for a flight aggregator example. Indeed, the servers are meant to receive a huge amount of concurrent requests, 1 per user of the website. So even if we just block 1 thread per request, it will degrade the performance considerably. So this means that the only way to make I/O viable for concurrent programming is to make it non-blocking, similar to how futures work. This is what we're going to do in the next video. See you soon.